So far we have discussed about some exact solutions of the Navier-Stokes equation, but with a consideration that there is a single phase flow. However, there are many practical applications in science and engineering where there are multiple physical phases present. So, when there are multiple physical phases present, it is very likely that there is supposed to be an interface between the two phases. So, today we will try to understand how to broadly treat flows with interfaces. Let me give you an example and we will mainly consider that example in this module, that you have a liquid and you have air and there is an interface between liquid and air. In general, this could be generalized as fluid 1 and this is fluid 2. So, we will try to understand that what type of boundary condition we should give at the interface between the two fluids. There are certain important types of boundary conditions which we give for a fluid, single phase fluid on a solid boundary, and one such boundary condition is no slip boundary condition. I will not discuss about the no slip boundary condition in much details today, because the no slip boundary condition is I mean of course debated over micro and nano length scales, but on an average for many engineering problems it is a correct way of giving the boundary condition. But more importantly, what can be said is that there is another boundary condition at the interface which of course is never debated and which is always valid irrespective of the considerations of slip or no slip at the boundary. So, the slip and no slip, it talks about the tangential component of velocity, but there is another component which comes into existence and that is the normal component of velocity. And we say that if there is a solid boundary, I am giving you an example. So, this is solid boundary is like phase 1 and liquid is phase 2, and if there are no holes in the solid, then the fluid cannot penetrate the solid boundary. The very fact that the fluid cannot penetrate the solid boundary is called as no penetration boundary condition. So, no penetration boundary condition means there is no normal component of velocity across the interface if the interface has if the solid boundary has no holes. Question is, instead of a solid boundary, if you have a boundary like this and the difference between this solid boundary and this boundary, this we have to conceptually understand very carefully. This is a boundary which can dynamically evolve. So, this discussion not only pertains to the boundary between two fluids, it could also be boundary between two elastic or flexible phases. So, the whole idea is that this is a rigid wall, instead of a rigid wall you have a interface that is so flexible that it evolves over space and time, and that we call as an interface. So, in that interface, instead of the no penetration boundary condition, we use a different type of representation of something which is a generalization of the no penetration boundary condition, and that is called as kinematic boundary condition. So, we will first discuss about the kinematic boundary condition. Kinematic boundary condition at the interface. So, let the interface be defined by a function of x, y, z and time. Now, physically, if you are sitting on the interface, try to understand the concept very carefully. If you are sitting on the interface, you will find yourself always located on the interface, no matter how the interface is evolving, because you are sitting on that interface itself. So, that means there will be no total change in f. In other words, the total derivative of f with respect to time equal to 0. So, this total derivative means this Vs is the velocity of a point located at any point S on the interface. So, this is the short form of a velocity called as surface velocity. Question is this velocity same as that of the fluid velocity? This velocity is same as that of the fluid velocity when there is no net mass flux across the interface, right. So, when there is, that means these two phases for example are immiscible phases, that is they do not mix with each other, then there is no net mass flux across the interface, and then Vs is equal to V. So, Vs is equal to V of the fluid when there is no net mass flux across the interface. But when there is a mass flux across the interface, what will you do? You have to find out what is the mass flux across the interface. Now, let us say that UR is the normal, or UN, or rather UR in the normal direction is the net velocity across the interface. So, that is basically the velocity of fluid relative to the point on the surface. So, that is the velocity of fluid minus velocity of a point on the interface. So, this is why we are making a dot with n, because it is the normal component of the interface velocity. N is the normal vector at the interface, unit vector in the normal direction, that is giving the net flux. So, now from this equation you can write the normal direction also can be written as grad f by mod of grad f, right. This is why, because gradient of a function, scalar function, physically denotes a direction normal to the surface representation of the function. So, you can write right. So, that means you can write Vs dot okay. So, now you can write in place of this, you can substitute this. So, if you know the fluid velocity, if you know this, then you can express the relative velocity in terms of this, and mass flux across the interface, that is mass flow rate per unit area, mass flux. So, normally this is what is the parameter of interest physically, what is the mass flux across the interface. So, that you can write in terms of rho into the relative velocity, and the relative velocity you can write the fluid velocity minus a velocity of a point on a surface, and velocity of a point on a surface normal component you can write in terms of the interface topology. So, in a special case when you have Vs is equal to V, then this UR is equal to 0, and when Vs is equal to V, you have the kinematic boundary condition as del F del T plus V dot grad F equal to 0. So, let me write that for two immiscible fluids, Vs is equal to V, that means there is no net mass flux, that means del F del T plus V dot grad F equal to 0 at the interface. Okay. So, for a flat solid boundary and or for a solid boundary that is not dynamically evolving with time, or in other words for any boundary which does not evolve with time and space, you have del F del T equal to 0 and grad F equal to 0. That means the normal component of V will be or in other words, let me write it in a different way. So, if you have del F del T is equal to 0, that means the boundary is not evolving with time, then V dot grad F equal to 0, and grad F is related to the normal component of velocity. So, this is actually V dot normal component equal to 0, unit normal vector equal to 0. So, this is the no penetration boundary condition. So, you can see that the no penetration boundary condition is a specific case or special case of the kinematic boundary condition. Now, so far we have discussed about the kinematics at the interface, but what about the forces at the interface? So, regarding the forces, there would be a tangential force balance and there should be a normal force balance. So, when you come to the force balance conditions at the interface, then the first question comes, what are the forces? So, if you consider the forces acting on the interface, one of the very interesting components of forces that comes into the picture is the surface tension force. So, surface tension force, how do you quantify the surface tension force, or how do you physically describe the surface tension force? Let us say there is an interface, there is liquid and there is a gas phase which can itself be a vapor. So, now in the liquid side you have molecules, these molecules will be very densely packed. On the other hand, on the gas side there will be molecules, those will be not so closely packed. So, if there is a molecule here, because of the very dense packing of the molecules here, it will be attracted more severely towards the liquid side than towards the gas side. If it so happens, then this will actually have a tendency to get dissolved in the liquid until and unless there is a force which, or there is some energy at the interface which holds the capability of holding it at the interface and not allowing it to dissolve in the liquid, otherwise interface will not be formed, and that energy of the interface is called as the surface energy. And because you know there is a net force acting inwards, the interface is always appearing to be in some kind of tension. So, this energy is equivalently expressed as a force per unit length, and that force is called as surface tension force. And so, it depends on the phases. So, for example, if there are two phases, liquid and gas, then normally we write the sigma L G or GL. So, we designate by these two phases. For an interfacial boundary condition like this, normally what we do is that we write it simply as sigma with an understanding that it is between a liquid and a gas phase, or maybe between one fluid phase and another fluid phase. But you have to remember that sigma is very much there between a liquid and a solid phase and a gas and a solid phase, because it all arises as a combination of or as a culmination of attractive and repulsive interactions and adhesive and cohesive forces as a gross manifestation of that. Therefore, it is there at all interfaces. So, now so the unit of this is Newton per meter. So, now if you have an interface, we will first try to understand that if the interface is in static equilibrium, what are the forces acting on the interface. So, let us take an example. Interface in static equilibrium. So, when there is an interface in static equilibrium, what we do? Let us say that there is a membrane. I am just drawing a simplified picture for your understanding, which has basically one radius of curvature along one side, which is R1, and another radius of curvature along another side, that is R2. So, let us concentrate on this R1 and let us say this is the center of curvature. So, after some time this membrane is stretched and it comes to a new configuration, which I will try to show with a different color. Just arbitrarily like this. This is the new configuration of the interface. So, let us say that this dimension was x, this dimension was y, and this now has become x plus delta x, this has become y plus delta y. As I told that we will consider R1 as the radius of curvature of one side. I will try to draw it with some particular color. This is R1 and let us say this is delta x, this is a magnified delta z, this is a magnified figure just to indicate that you have a change in the membrane area. So, a membrane is stretching. So, when the membrane is stretching, there is a work done because of stretching of a membrane. So, why this work is done because of the stretching of a membrane, or what accounts for this work? Actually, because of the curvature of the membrane, there is a pressure difference across the interface, and we will soon see that why this curvature gives rise to a pressure difference across the interface. So, when you have, so let us for the time being assume that delta P is the pressure difference across the interface. So, when you have delta P as the pressure difference across the interface, you multiply this delta P with the area to get the resultant force which is there across the interface, and this force times the displacement, virtual displacement delta z. Of course, virtual displacement we give a different symbol, but I am just conceptually doing it without getting into the rigor of writing it properly. So, this work done, how does this interface do this work? So, there understand there is a pressure difference across the interface still the membrane stretches. So, that means it must have sufficient energy so that it uses that energy to do the work in presence of the pressure difference. So, what is that energy? That energy is nothing but the surface energy. The surface energy is the surface tension times the change in area. So, the change in area is x plus delta x into y plus delta y minus xy. Okay. So, this is sigma. When you write sigma, this is sigma between the two phases. So, it is if one side is liquid, another side is vapor, then sigma LV. So, x plus delta x into y plus delta y. So, xy plus x delta y plus y delta x plus delta x delta y, this we neglect because this is very small, minus xy. So, you can write this equation delta P is equal to, so I am just isolating it because otherwise it looks like the part of the same equation. So, delta P is equal to sigma into this is y delta x delta y by x y delta z plus y delta x by x y delta z. So, x you cancel and here y you cancel. So, now from similar triangles I will just quickly tell what are these triangles for which we are talking about the similarity. This small triangle and this big triangle. So, from the similarity of these two triangles we can write R1 by R1 plus delta z is equal to x by x plus delta x, simple ratio proportion. So, that means R1 by delta z is equal to x by delta x. So, we can write delta x by x delta z is 1 by R1. So, this becomes 1 by R1, simply this will become 1 by R2 in a similar way. So, the pressure difference across the interface is under static condition is delta P is equal to sigma into 1 by R1 plus 1 by R2, where R1 and R2 are the radius of curvature of the respective elements. So, this element has radius of curvature R1, this element, and this element has radius of curvature R2. Now, the question is, this is under static equilibrium. So, from here we can say that if the interface is flat, then R1 and R2 are tending to infinity. So, 1 by R1 and 1 by R2 will be 0, that means there is no pressure difference across the interface. However, if the interface is curved, then you can write delta P is equal to this. Now, in dynamic condition what will happen? In dynamic condition this delta P will be supplemented by a viscous normal stress. So, delta P, so you will have delta P minus the normal component of viscous stress. So, the traction vector the viscous element of the traction vector or the deviatoric component of the traction vector this is normal stress balance. So, what we have done under static condition this term is not there, under dynamic condition we have added, this is the traction vector, we have already discussed that, V for viscous. So, only we are taking the viscous terms because the hydrostatic component is already taken here. So, this has to be the deviatoric, dot with the normal is the normal component. Why minus here? Because pressure by its positive sign convention is compressive, whereas this by positive sign convention is tensile. So, the only difference between the static and the dynamic condition is that you add this so called viscous normal stress, and this is something which we have to keep in mind, is very non-intuitive. Normally we have a belief that viscosity gives rise to shear stress, and that is how the topic of viscosity is introduced in undergraduate classes, but viscosity can also give rise to normal stress, and we have seen how it is possible through detailed derivation of the Navier-Stokes equation that we have done earlier. So, this is a normal stress balance. or a normal force balance. So, the final issue of the interfacial flows is the tangential force balance, and we will come to that now. So, for tangential force balance, again we will consider a flat interface. Tangential force balance. Example, flat interface. So, if you have an interface like this, let us say this is an interface, this length is L and this length is dx. Let us say the net shear stress acting on the interface is tau. This is the net, means actually this is the difference between the shear stress looked from one side and the shear, maybe shear stress at the top and shear stress at the bottom. If the top phase is a gas phase and the bottom phase is a liquid phase, normally because the viscosity of the gas is much less than the viscosity of the liquid, we neglect the shear stress in the gas phase, and then this becomes the shear stress in the liquid phase only. Otherwise, this tau has to be interpreted as the difference in shear stress across the two sides of the interface that you get. So, the corresponding force is tau dx into L, shear force times the area. What about the surface tension force? So, here it is sigma into L, here it is sigma plus d sigma into L. So, how can sigma change? The surface tension can change, maybe because from here to here you have a temperature gradient. This is known as Marangoni effect. So, you have change in surface tension due to change in temperature. You could have a change in surface tension due to change in chemical composition also. So, there could be many possibilities. So, you can write a force balance at the interface. So, you can write tau from this, from the balance of these three forces you can write tau is equal to d sigma dx. What if the interface is curved? If the interface is curved like this, then instead of x you have to deal with a unit vector in the direction s and unit vector in the direction n. So, you can write in place of tau it will be t, the traction vector, dot s. So, what we have done is we have taken the s component, the tangential component of the stress which is coming through the traction vector is a gradient operated on sigma. This is called as surface gradient dot with s, because it is in the direction of s, the force in the direction of s. So, what is grad s? So, let us just take an example. So, this is curved interface, this is not flat interface, because here we have taken the s and n direction. So, to understand how to write an expression for grad s, let us say we write an expression for acceleration along x, just it is a different analogy altogether. So, acceleration along s is acceleration minus acceleration along n. So, this is a minus n dot a n, right. This is the normal component and this is multiplied with n is the vector representation. So, similarly you have grad s is equal to grad minus this is the expression for grad s in terms of the grad or So, you can see, to sum it up, across the interface we have discussed about 3 important boundary conditions. One is the kinematic boundary condition, which for a special case becomes the no penetration boundary condition, then a normal force balance and a tangential force balance. And these balance conditions at the interface are very important to write the hydrodynamics at the interface. When there is another additional field, for example there is an electric field, then this traction vector has to be augmented with the stress due to electrical field, and that corresponding stress is called as Maxwell stress or electrical stress. We will not consider that as a part of this course, but I am just giving you an idea that how to enhance this fundamental understanding of how to write boundary conditions across the interface to solve more complicated problems, where you also have other physical effects like, for example, electrical effects, magnetic effects and so on. Thank you very much.